Okay, so we'll get started. For the next 2 lectures, we'll be talking about nuclear chemistry. Previous chapter, we've been dealing with chemical reactions, right? So when we think about bond forming and bond breaking, that has to do with the interaction between the electrons of each element. So the identity of element generally doesn't change in chemical reaction. But however, for nuclear chemistry, it's dealing with change in the elements. If you recall the earlier chapter, as early as chapter 1 and chapter 2, when we describe the periodic table, we think about the atomic number, right? So atomic number reflects the possible identity or possible reactivity of these elements. For nuclear chemistry, I want you guys to think about the structure of an atom. Within the middle part of an atom, there is a nucleus, right? From the previous chapter, we learned that nucleus is what's responsible for keeping these electrons around the nucleus. Okay, so nucleus is very small and very dense. Okay, so the focus of nuclear chemistry is the study of how we can utilize the power of nucleus. And of course, when we talk about nuclear, a lot of time you will think of nuclear power plants, right? So Taiwan has 3 of those that generate a lot of electricity based on the nuclear chain reaction. For the next lecture, we'll be talking about nuclear fusion and fission. One of those is a process that utilized to operate nuclear power plants. And also, we know that there's nuclear bomb, right? They're atomic bomb. So we can generate a lot of energy from these reactions, okay? So that involves the change in its element identity, and it releases a lot of energy. So you can think of nucleus as a very high energy species, but usually it's not reactive unless there's under certain condition or a certain composition. It will render these atoms unstable. We know some nuclei are unstable. Previously, we learned about the concept of isotopes. So if you remember, what are isotopes? I want you guys to discuss with your partner and see if you can come up with a few criteria that determine 2 species are isotopes to each other. So the isotope should have the same atomic number, but its mass number may be different, right? So a really good example would be various type of chlorine species. And then we know the molecular weight of chlorine is usually 35.5, right? That is because we will take the natural distribution of these isotopes and we calculate the average molecular weight, and that's where all these things come from. So here, this is what we call the mass number, and this is the atomic number. And we'll come back to this definition in a little bit. For a nuclear reaction, so usually it involves radioactive decay. I know you guys heard the term radiation, right? A radiation is a form of energy. For the unstable nuclei, when they decompose, it will generate some radiation. And there are many types of radiation, or you can think of it as an emission of some sort of energy. Okay, for the chemical reaction, is generally its rate is affected by temperature or catalyst or even pressure, right? So a distinct difference between nuclear reaction versus chemical reaction is that nuclear reaction is not dependent on temperature, catalyst, or pressure. So if you can look at your table 24.1 in your textbook, there is a comparison between chemical and the nuclear reaction. Take a minute to look at the difference between those 2. So previously, Rutherford have done the gold foil experiment. And then in that session, we basically tell you the result that he found. When he utilized a device that generates alpha particles. What are alpha particles? We didn't really define what it is, but we know it's from a radioactive material, okay? So it can generate alpha particles. So what are alpha particles? It can be represented as a charged helium species or a simply alpha. And then you recognize that there is mass number and atomic number. Okay, so it is a form of energy that is emitted during the radioactive decay. If you remember the gold foil experiment, most of the alpha particle go through the gold foil, but the very tiny amount, it will hit the nucleus and get deflected back. Okay, so you remember that gold foil experiment? Most of most of response from your detector, this photographic film, most alpha particle hit here, but when you hit the nucleus of your gold atom, it deflects back. Okay, so Rutherford confirmed the presence of nucleus. Let's go back to a little bit of history. So in 1895, X-ray was discovered. There's a scientist found that when he can see his skeleton under X-ray. Okay, so then people are begun the search for other radioactive materials. And then a French scientist in the year later discovered uranium. Then there's uranium mineral. And this is a main component or a radioactive material used for power plants and making nuclear bomb. Usually this is present as in its oxide form. This oxide, uranium ore, can be found in nature. Okay, and then generally they're in Congo, which is a country in Africa, and Canada. So back in the days, people were learning, they know these minerals are radioactive. They start beginning to try to isolate the element out of it. Remember electrolysis from previous chapter? Okay, so Marie Curie, the first woman that got Nobel Prize. So back in the day, there were very few women in the field of science, but Marie Curie managed to receive 2 Nobel Prizes, okay, one in chemistry, one in physics, for her discovery of radioactivity and her discovery of 2 elements. So she discovered this one, the polonium, because she's Polish, so this is in honor of her country, and it has an atomic number of 84. And she also discovered radium, which has an atomic number 88. So back in the day, the periodic table is not complete, okay? There are still a lot of missing spots, but Mendeleev predicted that, okay, we're gonna have all these elements. And as you can see here, down here, several of them, for example, the berkelium, okay? These are man-made elements, because they studied nearby Berkeley, and there's a research institute that they work with high energy physics. Well, like a lot of these are man-made, okay? So Marie Curie, she was studying a uranium ore and learning how can you isolate radium from these minerals, okay? So she herself is working with tons of uranium ore and then finally isolated 0.1 gram of radium by electrolytic reactions. So basically she melted these oxide at very high temperature and apply electricity to it, and they're able to isolate the element. Okay, it's a very complicated process. It's hard to imagine someone would be doing stuff like this nowadays. But however, Marie Curie managed to do that. And her discovery is that she thinks the radiation must come from the atom itself. So her husband at the time, Curie, together they developed electrometer. So that allows one to measure the electrical charge. And then more importantly, she found that intensity of radiation is directly proportional to the concentration of element. in the mineral and not to the formula of mineral. That is a very important criteria. So the radiation is really coming from the decomposition of certain elements. So let's go back to uranium. In your textbook, it's called the pitch blende. And this is also known as uranite. Okay, so we know like in Iran, they've been actively doing nuclear research. They're trying to have the technology of nuclear bomb. So in Taiwan, actually, at Tsinghua University, there used to be a department called nuclear science. Okay, so Taiwan at one point was also trying to develop nuclear weapons. However, that program got shut down. Okay, so now the department is restructured into two different institutes at Tsinghua University. So one is the Yihuan所, and the other one become 工业科学, something like that. Okay, so anyway, from this mineral, generally there's a lot of oxide species. Okay, so upon reaction with fluorine-containing compound, you can generate uranium fluoride, which is the gas. Okay, and then as I mentioned, based on the mass number, okay, so we learned that the diffusion, or in the kinetic gas theory, the kinetic energy is proportional to the molecular weight, right? So by doing a very complicated gas separation process, you can separate these isotopes. Okay, so they were managed to use gas diffusion to enrich uranium, because there are certain type of uranium is stable and certain type of uranium is unstable, right? Certain isotopes. So that is why I call the uranium enrichment process. So for conventional electric power plant or nuclear reactor, about 20% of that uranium is 235, okay? So this is the radioactive version of it. But if you want to make a nuclear bomb, okay, that has to be a very highly concentrated. Okay, so you will see the word yellow cake if you look into how the uranium is being recovered from its natural form, which is the uranite. Okay, so you undergo many complicated isolation process. So Richard Feynman, very famous physicist, was actually had a very interesting book that talks about his experience with development of nuclear weapon. Okay, so because during World War II, actually there's a lot of physicists were recruited to New Mexico. So that's where they were undergoing a very classified military research. So nobody really know what they're doing, other than they're knowing part of this program where they're trying to enrich uranium or trying to isolate these radioactive compounds. Okay. So let's go back to Mary Curie, or sometimes refer her as Madame Curie. She's both physicist and chemist. So she also initiated IUPAC, which is an organization that is known for coming up with names for newly found compounds. Okay, so she referred emission as radioactive emission as radioactivity. Okay, and then more importantly, after she successfully isolated pure radium, as I said before, she only got 0.1 gram from several tons of minerals. She noticed that there are other elements formed when the radium decay. So that is a very important observation. Okay, now we'll talk about different type of radiation. So previously we talked about alpha particles. Okay, so that is one form of radiation. And other kinds include beta, which is generally the high-speed electron. Okay, and then another form is gamma ray. And in this case, this one doesn't change the atomic number or change the mass number. You can think of it as just a form of energy when an element undergoes the radioactive decay. Okay, so anybody know what gamma ray is used for? So certainly gamma ray is a high energy photons. Okay, so you can induce some chemical reaction with gamma ray. And also it has a very deep penetration depth. about 10 centimeter. So you can use gamma ray for some medical applications. All right, so we'll get to the applications of these gamma ray or other type of decay in the next lecture. So for the beta, I forgot to write. It had the -1 here, and I know it looks confusing. Why the electron is -1? It will make more sense when we actually look at different type of radioactive decay. So I would like to direct your attention to table 24.2. So I know several of you are already on that page. That is a very nice figure that shows different kind of processes. So it's on page 1076. So noticing the change in the color upon the radioactive decay. And if you flip to page 1078, it has a summary of each of these decay and how that would affect your A and Z. And notably, we know when you change your atomic number, you're expected to have different reactivity, right? It becomes another element. Okay, so from these, regardless if it's alpha decay or beta decay, generally you'll be making elements that has atomic number that one higher or one lower, depending on which kind of beta decay it is. Or the atomic mass can change by 2 if it undergo alpha decay. So a very important example, let's go back to radium. For a radioactive form, isotope of radium, right, it will decompose into another element accompanied with the generation of alpha particles. Okay, so recognizing that this is the calculation that you may see on the test, to test for knowledge. So this is also the conservation of mass number and atomic number. You cannot just destroy an electron, right? You cannot just destroy a neutron. They have to go somewhere. So when it decomposes, you recognize here the total number of mass number needs to add up for your product, okay? And total atomic number should add up, okay? And then you should be able to recognize whether this is the alpha or beta. So it basically differs in atomic number. So let's look at an example of beta particle decay. So beta particle decay, one very important example is where carbon-14 will go to 14. And this beta particle that has a -1, right? If you -1, it becomes 6, right? Okay, so carbon-14 is a very important isotope. It's used for, you probably heard of carbon-14 dating. So that means you can determine how old an object is based on the amount of carbon-14. Okay, so you may wonder, where did carbon-14 come from? Okay, so we know in the atmosphere we have a lot of nitrogen, right? So actually it's a very high energy called the cosmic rays. Okay, so cosmic ray is a very high energy photons that moves at the speed of light. I know it's hard to imagine what it is. For the physics major, you guys will study cosmic ray in more details in your more advanced courses. A cosmic ray comes from supernova explosion of stars. I don't even know what that means, but so basically when there's these explosion happen in the space, it generates these very high energy. Or in some movie, you will see, someone being irradiated with cosmic ray, and then all of a sudden they have superpowers, right? Okay, so anyway, with the presence of cosmic ray, it can convert nitrogen into carbon-14. So it's everywhere. But the precision is not so high, okay? Because there are going to be some variation depending on how you analyze your sample and how the sample is being preserved, because it can be contaminated with other substance. So when you calculate the amount of isotope of carbon, it may not be accurate, okay? Okay, so let's look at another example of beta particle emission. Let's look at nickel. It can form copper. Okay, so this is the emission of beta particle. So for the beta decay, there's three forms. Beta particle being one, okay? And then there's another thing called the positron. Okay, so an example of positron is that we starting from carbon 11, it undergo decay, generate boron, but noticing that mass number doesn't change, but the atomic number change. That's why it's boron. And noticing that positron here is 1, okay? So you go from a higher atomic number to a lower atomic number. Here is going from a lower to higher. So that is different between beta particle and positron. Okay, this is just to account for the flow of energy. Okay, so each of these products have energies. So think about chemical reaction, right? So every substance had its states of energy for its own existence. Okay. Now we can talk about electron capture. So that is, again, it's a very high energy electron. Where does mass number come from? It has to do with the composition of your atom, right? So electron capture. So basically it converts a proton to a neutron, okay? So an example is where you have iron and then generate another element, and then the extra energy would be X-rays. Okay, so this is just extra energy, and how will we know it is X-ray or not? We look at the wavelengths, right? So for the different kind of light, right, there's different wavelength. Okay, so that is the main process that generates. You inject a very high energy electron into your atom, end up generating the excess energy. And noting that, I mean, the mass number doesn't change, but the atomic number change in this process. Okay, so generally you can recognize the pattern for the beta particle or the beta decay of different elements, right? So basically you change your atomic number, but your mass number is generally the same, and then you just emit a package of energy out during these processes. So gamma ray, it's also generated when a particle and antiparticle combine. So how is gamma ray useful? So I previously mentioned there are some medical applications, right? So for example, there's something called the positron emission tomography. Okay, so it's basically using radioactive compounds such as, we know, fluorine. The molecular weight is usually 19, right? Okay, so but we can use fluorine 18, okay, and then label your glucose. And we know the cancerous cells, they need a lot of energy, right? So it utilizes a lot of sugar. So we can label glucose, but since it looks like glucose, but so your body, your metabolism system will process such chemical, right? So based on where these things go, it will emit gamma ray, right? And then so you can detect that signal, and then we know if there's abnormal distribution, then it could indicate there's potential cancerous cells in certain part of your body. Also, we know oxygen, usually molecular weight is 16, right? But you can use oxygen 15. You can make water with oxygen 15, and you can use that to monitor blood flow. Let's look at this iron. How do we know if something is stable or not? So let's look at page 1079. You can calculate the amount of neutrons and the amount of protons that you have, right? The proton is the Z value, which is your atomic number, right? So here's the several scenario. If you look at the figure 24.2, the black dots are referring to the stable isotopes. Okay, and then so there's a very narrow band of stability. Okay, so if you are not within that band, it either undergo beta decay or the positron emission or electron capture. So there's different mechanism. Okay, so why does radioactive species, they want to decay? So you can think about why reactions happen, right? Everything wants to go to its lowest energy state. You can think about thermodynamics, right? It wants to increase the entropy, right? So it wants to release this extra energy to the surrounding. So there are several criteria. So when n equals to z, generally they're stable. And if your n number is larger or smaller than z, you will have radioactive decay. Okay, and then generally for elements with a z larger than 83, a lot of them are unstable. So 83 it's already down here. Okay, and then so there's a footnote in the book that's saying that some isotope of this bismuth is still capable of undergoing alpha decay, but it's doing it at a very, very slow rate. So when we're talking about rate, remember the concept of half-life from the chemical reactions? Okay, so for the radioactive decay, you can assume it's a first-order reaction. And if you flip to your textbook on page 1084, so I know the notation is a little different, but generally, so if you flip to 1086, there's a calculation of decay, right? So we can, using simple first order rate law, to figure out the half-life, right? And then we can, from the half-life, we can figure out after a certain amount of time how much your radioactive species has decomposed into its lower energy states. Right, so the math is quite simple, and that is, so you basically use natural log of 2 divided by your half-life, and then you can solve for the remaining compound after a certain time. So I want you guys to look at the sample problem 24.5 and just kind of go through it.